talk about a tough sell. Mathematical logic. For many people, there's only one thing more frightening, more to be dreaded and feared than mathematics. I don't even want to say its name. It's the name of the constellation between Gemini and Leo. Think of it. Oh, it's not Scorpius. Scorpions are dreadful enough and very frightening. But between Gemini and Leo, it's hardly a constellation at all. It's more a blank spot with the name of Cancer. And as far as the word logic goes, there's only one thing more arid, more lifeless than logic. The Sahara Desert. And so, for many, many people, there can be only one thing more dreadful than a presentation on mathematical logic. A series of presentations on mathematical logic. I asked the members of the audience to put away all such negative conceptions, which surely are the result of how these topics are taught rather than the topics themselves. Mathematical logic contains within it some of the most awesome results in all of mathematics. It has a useful and a practical side, and it is an important subject in its own right. Several people who were members of the audience when these presentations were delivered live have told me that the content of these presentations is quite good. Several were recorded twice in different venues so that the recording of the higher quality could be the one put forth for public view. In assembling these materials into a finished product, some of the transitions might be abrupt indeed. In all, the sheer quality of these presentations does not match and cannot match that of a professionally run television or movie studio. But you will be hard-pressed to find material more thought-provoking or more majestic than mathematical logic, the content of these presentations. And with that as introduction, we proceed now to the first episode. Let us proceed. Mathematical logic has produced many splendid results. This series of presentations is intended to show some of the striking and important, but still theoretical results that mathematical logic has achieved, especially the splendid theorems of Gödel. But mathematical logic currently lags in practicality. Toward the end of this series, we shall go further. We shall show how mathematical logic can become practical in a way that has never before been seen. The sheer user hostility of the traditional formalization precluded its being functional. We solve this problem by changing the formalization of mathematics at the level of phrase structure. A journey of 1,000 miles begins with the first step. Again, I say, let us proceed. We skip an enormous amount of history of the subject, the work of Aristotle on syllogisms, the work of the Middle Ages, where syllogisms were exhaustively treated and classified, the work of George Boole, who made the propositional calculus resemble a form of abstract algebra. We skip the work of many others, all worthy of the mention I am not giving them. We go straight to the result that forever changed logic into its modern form. Russell's paradox. I'll state it here. 'Tis absurd to create sets with wild abandon, such as creating the set of all sets, or creating the set of all sets that are not elements of themselves. I should digress. This result came about in the 1880s or so, I do believe. 'Tis absurd to create sets with wild abandon. Who would think? I'll present the proof. It's very important. For as proof, assume, if possible, that it were not absurd to create sets with wild abandon. Consequently, create the set V to be the set of all sets. Surely V is an element of V, since V is the set of all sets, and V is itself a set. Well, that certainly is unusual, a set to be an element of itself. We even give it a name. A set, by definition, is extraordinary if and only if your set X is an element of its own self. A set is ordinary if and only if your set X is not an element of its own self. Clearly, every set is either ordinary or extraordinary, not one or the other, but not both. This should be familiar territory for most math professors, but it's so fundamental we're reviewing it here and learning it if you don't know it already. Since we are creating sets with wild abandon, we can create the set foo, or full of ordinariness. It is the set of all ordinary sets. The set full of ordinariness has, as elements, all ordinary sets and no others. All extraordinary sets are not allowed to be members of full of ordinariness. For all sets X, X is a member of full of ordinariness if and only if X is ordinary. This is the same information over and over again, just to make sure you have it down pat. Now, this slide I'm presenting here, if you want, you may pause on it and spend 15 minutes of your life poring over it until you have the proof down pat. It's a wonderful argument, well worth any student of mathematics to know, but this argument is briefer, it is often used, and may be more convincing. For all sets X, X is an element of full of ordinariness if and only if X is not an element of its own self. That's how we define full of ordinariness. Since we are creating sets with wild abandon, full of ordinariness is a set. Here we see a major premise, a minor premise. Let's go to the conclusion. Wrong syllogism. Therefore, foo is an element of foo if and only if foo is not an element of foo. Just put full of ordinariness in for X in this line. Full of ordinariness is an element of full of ordinariness if and only if full of ordinariness is not an element of full of ordinariness. This line right here. And I hope everybody can recognize that as absurd. That is impossible by sheer logic. Now, in this proof by contradiction, everything inside a proof by contradiction has no reason to be true, and usually isn't. Anything constructed inside a proof by contradiction has no reason to exist, and often doesn't. So this use of Brown type just lets you know anything in Brown type, don't think it exists. We have no reason to believe so. It's inside a proof by contradiction. Well, we've done our proof by contradiction. Let's close shop here on this theorem. Therefore, it is absurd to create sets with wild abandon, such as creating the set of all sets, or creating the set of all those sets that are not elements of themselves, which was to be demonstrated. Russell's paradox presented as a theorem with its proof. And again, this is the beginning of modern logic. Now, one can form positive and form negative views of Russell's paradox. On its face, Russell's paradox is surely negative. It tells what you cannot do. One can even have a gloom and doom attitude. For example, that the paradox shows an essential contradiction in mathematics, that there is a fundamental flaw in mathematics, that there's a hole at the bottom of mathematics, and so forth. But a positive view is possible. After knowing what you cannot do, look to see what you can. Bertrand Russell did not wallow in negativity, though he could have. He produced positive results and led others to the completion of the work. Much to his credit, Bertrand Russell worked with Alfred North Whitehead to produce the somewhat vainly titled work Principia Mathematica, same title as what Newton chose for his. It's a little, quite a title. This work, though, showed how to form mathematics in a graded fashion so as to be free of paradoxes and contradictions. This work, almost everybody calls it a Peano version. It was refined and extended by Zermelo and Fraenkel in the 1920s and 30s to form the famous ZF axiomatization of set theory. This formulation is standard even to this day, 100 years after it was published. Now we move to statements. There will be a more specific definition later, but a statement generally is an expression that is either true or false, though which it is may depend on variables. A closed statement is a statement that by sheer grammar does not depend on any variables. This occurs when all its variables are quantified. For example, in this statement here, for all real numbers x, the square of x plus 1 is x squared plus 26 plus 1. I must warn you, when we do these fundamentals, the examples we choose can frequently be of very low-lying stuff. We're trying to get underneath them. An open statement is simply a statement that is not closed. False statements pose no theoretical difficulty to these systems, though they may bother moralists on occasion. Any number of little jokes about what goes on in Washington, D.C. about people not having any difficulty with false statements could be made here, but we shall pass over. We move now to the liar paradox. It was old even in the days of classical antiquity. It may be thought of as Russell's paradox applied to statements, though it is far, far anterior by many centuries. Consider what's in this box. This statement is false. If this statement here is true, then it's true that it is false, and so it is false. See that? And so if it's true, then it's false, a contradiction. Put it on brown type, probably. Oh, so surely, since it's not true, it must be false. Well, if it's false, then it's false that it is false, and so it's true. So if it's false, it is true. Another contradiction. This is a paradox that has caused much ink to be spilled, and many have worked on it. I will resolve it in the next slide. Let's take a look at this thing. This statement is false. The text in this box is indeed a fraud, but not where you would expect. We have just shown that the text in the box cannot be true, and it cannot be false. But statements are either true or false, but the thing in the box is neither. Consequently, the text in the box is not a statement, though it advertises itself to be. It looks like a statement because it has a subject and a verb in the indicative mood and all the rest, but it is not and cannot be, in fact, a statement. This brings us to another paradox, the truth-teller paradox. I've not seen this in the literature. I hope I'm not the first one to see it. But let's take a look at this one. This statement is true. Much more positive, don't you think? The text in the box is also a fraud, but in a different manner. Suppose, if possible, that the text in the box were a statement. Then its negation would also be a statement, since the space of statements is closed under negation. Thus, this statement is not true would be a statement. Just negate it, you get a statement. Thus, this statement is false would be a statement. But as we've just seen, this statement is false is not a statement. So it's a statement and not a statement at the same time, which is impossible. Thus, the text, this statement is true, is not a statement, and the fraud is It's asserting itself to be a statement. There's the fraudulent nature of it. Therefore, it is absurd to create statements with wild abandon, such as creating the statement which asserts its own falsehood, or even creating the statement which asserts its own truth, which was to be demonstrated. The Liar paradox basically turned into a theorem and proved. Now, how do we avoid Russell-type paradoxes for statements? In mathematical logic, one never makes statements about statements as such. One must always introduce a gradation. One may make meta-statements about ground-level statements. It is widely believed that at the slightest blurring of the line between ground-level mathematics and meta-mathematics, a Russell-type paradox is waiting to pounce, throwing the whole system into contradiction. Now, this distinction between the ground level and meta level of mathematics is a very standard issue for mathematical logic. It is absolutely necessary to avoid Russell-type paradoxes. The ground level of language of mathematics is machine-parsably rigorous and formal. You can program a computer to parse what is a ground-level statement and what is not. It contains the familiar operators of for all, for some, if then, if and only if, and, or, and all those Boolean things you know and love, negation, and backslash, the last of which performs substitutions. The meta-language is in English, if you speak English, or French, if you speak French, and all that. It is decidedly not machine-parsably rigorous. It is needed to speak of ground-level mathematics, otherwise we get a Russell-type paradoxes rising. It is needed to do mathematical logic at all. Now, the fact that this is decidedly not machine-parsably rigorous can cause some people a lot of cognitive angst. If your entire life was thinking that mathematics is just running through algorithms that a computer could perform just as well and in fact better, then you're feeling very, very uneasy about this. I'll just digress some. Back when I was in college, the professor of calculus had us do limits quite a lot. And that the sign of x, as x increases without bound, it has no limit. The limit as x increases without bound of sine of x does not exist. I had to just know that because I knew the sine function and knew what limits meant. I could not calculate myself to the answer. Well, whatever mental anguish that caused, I got over and have been doing mathematics ever since, but this is the nature of the beast. Let us talk now about ground-level proof. Ground-level proof is a string of statements, each of which is either an axiom or which follows from earlier statements in the string by any one of half a dozen rules of inference that are found on page 21 of Schoenfield's book. In the next presentation, I'll be trotting out a table of authorities, and you'll see all these books displayed before you. That's the definition of a ground-level proof. This formalization of ground-level proof will later be shown to be gravely deficient in that it does not model the manner of Euclid well at all, though it has been advertised to be so. It remains then very theoretical and impractical. Now let us move to Peano arithmetics. Peano arithmetic, what, 1880s or so? Someone in the audience correct me if I'm wrong. Let blackboard bold N be the set of natural numbers, a 0, and a 1, and a 2, and a 3, and a 4, and Sesame Street has a character to assist you with the rest. The set N of natural numbers, though infinite, is not created with wild abandon and gives rise to no Russell-type paradoxes. It has so been shown. Now, this statement there is actually far more controversial than you might think, and the substance of it, substantiating it, will be the substance of the second presentation. But for now, we're going to assume we can have whole numbers. Peano arithmetic also runs on some rudimentary logic and some common notions, though they are often called by another name. To construct conventional mathematics from Peano arithmetic, one must add some elementary set theory. This is done in Edmund Lundau's wonderful book, Foundations of Analysis, which I'll show you physically next time. The statements on the next slide are the Peano axioms, though slightly modernized. Recall, n is a set of whole numbers, starts with 0 and proceeds. The first axiom is 0 being a whole number, and it is. It's right there. The second axiom is that for every whole number x, add 1 to it, you get to a whole number every time, no matter how far out you are. The third axiom states that there does not exist a whole number x, so that x plus 1 lands you on 0. Look, negative 1 is not in the set. Yes. And starts at 0 and continues. The fourth axiom is this. For all whole numbers x and y, if you add 1 to each and you land on the same spot, you had to have started on the same spot. The converse of this implication is one of those common notions. If you start on the same spot, surely their successors must be on the same spot by even very low-level logic. Now we have this fifth axiom in quote marks. It's the principle of mathematical induction, familiar to anyone in higher mathematics at all. I state it here. For all statements A of n with a free variable n in them, if A is true at spot 0, and for all whole numbers k, if A is true at spot k, then A is true at spot k plus 1, the next spot. Then, for all whole numbers little n, A is true at spot n. Those of you who have seen the principle of mathematical induction will understand what I just said as fast as I just said it. Those of you who have not spent some time to think about it, is a very standard fixture in mathematics. But this axiom is put in quote marks. Edmund Lundau wrote before Russell's paradox. Edmund Lundau just put this as an axiom, but look, it has the word statements in it. This so-called axiom 5 cannot be an axiom in the ground language. It must reside in a meta language. So all you math majors, graduate students, and professors who've been afraid of mathematics, you've been doing it every time you've been doing proof by induction. You can't understand or even state proof by induction except by moving up to a meta language just to get it across. These are the very famous Peano axioms, and it's amazing that these axioms, together with some logic and set theory, can generate everything we know and love in conventional mathematics. Our next topic here is decidability. Remember that closed statements are those whose truth cannot depend on variables. They are either true or false, and if they're not either true or false, they are not statements. A separate issue is whether a statement can be proved true. This is, can we prove it true, can we prove it false, or do we acquit it for want of evidence? Something like that. A closed statement is called ground level decidable if, and only if, there's a ground level proof of A, or there's a ground level proof of the denial of A. You can prove it one way, or you can prove it the other way. We call such statements decidable. Otherwise, the closed statement is undecidable. Neither A nor its negation has a ground level proof. Now, when we teach mathematics, and most of you have only known mathematics as taught you, let's face it, we who teach mathematics tend to teach you only things that have already been proved. Yes, we don't send a bunch of open questions to you poor students in our classes. So this distinction rears its head when you understand mathematics to this level of detail. It's something that, if you think about it, yeah, it's always been an issue. There is a third possibility that must be taken into account. If both A and its negation have ground level proofs. You can prove the statement true and you can prove it false. Then the entire theory one is working in is called inconsistent. And everything about this inconsistent system is dismissed from further consideration. That's just how things work. A contradiction anywhere causes a contradiction everywhere. We just toss those out. So that's the definition for decidability. We are now in a position to understand, at least the statement, of Gödel's first incompleteness theorem. The first and second incompleteness theorems of Gödel are oft taken as the greatest theorems of all time in our discipline. Consider an axiom system that is consistent, computably axiomatized, and either is or has within it Peano arithmetic. So we have an axiom system with some axioms and some rules of inference, and we're getting it up and running. Consistent means that we cannot prove a contradiction. We cannot prove a statement true and prove the same statement not true. That just cannot be. Computably axiomatized means that a person can program an idealized computer to take a simple string as input, and the computer program works on it and will return a 1 if it is an axiom, or a 0 in all other cases, like it's not an axiom or it doesn't parse as a statement or any of those things. So this computably axiomatized axiom systems are standard. And suppose it either is or has within it Peano arithmetic, which is just about all mathematics most mathematicians are interested in. And I'll back up here to this so-called axiom 5. It's not a ground level axiom. For each statement A, this is an axiom. Let me just put this. If I blank out that line, all of this is in the ground language of mathematics. And so a very good programmer can see, oh, is this of this form for some statement A, and the space of statements has a very precise definition in the ground language. So this is a very common thing to happen. Axiom systems are normally like this. It's unusual for them not to be. Then there is a statement, A, in its ground language, both whose assertion and whose denial have no ground level proof in that system. There is a statement A in its ground language that is undecidable by the definition just given. This is an amazing, astounding result. Whenever I go through the details, the proof is by contradiction and is consequently non-constructive. Constructing such an undecidable assertion will be the topic of the next presentation, but this is where we are now. Now, the halting problem theorem of computer science is oft considered to be the analog of the first incompleteness theorem. Those of you in computer science should know that. Now, we have these consequences of the first incompleteness theorem. A corollary of the theorem, together with the details of its demonstration, is that the proofs of theorems in mathematics can be arbitrarily longer and more complicated than the statements of the theorems. And that's just an amazing thing. A statement of a certain length could have a proof of 10,000 million lines for all we know. In fact, the lengths of the proofs of statements in mathematics can be, in general, beyond all computation. And I'll just show you how that's a little, can be understood. The idea of computability is built into Gödel's incompleteness theorem. That's why we get these results about computation, can be beyond all computation. Another consequence of the first incompleteness theorem is this. No computer program can be devised that can act as a proof theorem. Again, these consequences take some proving of themselves. You have to really understand the theorem and the proof behind it to get these consequences, but it's true. No computer program can be devised that can act as a proof theorem. Even if the computer were to have an infinite amount of space in the form of memory, still such a computer cannot be programmed always to produce a proof or disproof of an assertion given arbitrarily to it as an input. Nor can you program it to compute even whether the assertion is undecidable. These inputs, of course, are symbol strings, very familiar to people of this generation. The idealized computer, though, is constrained to have an arbitrarily large, but still finite, amount of time in which to perform the computation. Again, very reasonable. If you have infinite amount of time, all sorts of things could happen. Now, we have these philosophical positions. Some people have taken the first incompleteness theorem to mean that there is an inherent fuzziness to the set of natural numbers. It is, after all, infinite. Though everyone must agree as to the assertions that are provable within the system, there are statements that are unprovable either way. And different people can have different notions of the whole number system concerning these finer, undecidable assertions. Just don't put them in the same room together and it should be okay. But other people believe that the whole number system is so firm a thing that closed statements in the ground language about it are unfailingly either true or false, even if we do not know which. For these people, the incompleteness theorem shows that there exists statements about the whole number systems which are in fact true, but which are not ground level provable from the Peano axioms. And furthermore, they are not ground level provable in any system whose axioms are both evidently true and can be computably recognized. Gödel, when he stated his theorem, he stated it in such generality that you think you're getting away, you're still in the boundaries of the generality in which Gödel stated his great theorem. For these people, these, quote, undecidable assertions are undecidable in the ground language only, because that was our definition of undecidability. Perhaps, just perhaps, they can be resolved in a meta-language. Searching for means of determining truth in mathematics must propel one to delve into the meta-language, since there can be no resolution of these, quote, undecidable assertions in the ground language. Full disclosure, I am a member of the second camp. One motivation for creating this series of videos is to demystify metamathematics so that it may be able to be used as a working tool. Hence the title of the series of presentations, Forging Ahead. We shall not get that far, oh, I wish I could. But by forging ahead, we shall do this. We shall use metamathematics to create a user-friendly, but still machine-parsably rigorous formalization for the logic undergirding conventional mathematics. Quite something, I think. But let us stop here and just take stock of where we've already got. We have laid some foundations in mathematical logic. We have produced a presentation of Russell's paradox and the liar paradox. We have shown what is the division between ground-level mathematics and metamathematics. We have shown the necessity of this gradation. We have defined ground-level proof. And, amazing, we have even shown, well, not shown, stated. We have stated Gödel's first incompleteness theorem and its consequences. The proof of Gödel's incompleteness theorems is quite something, which we will not be doing. The members of this audience should be well prepared to understand the subject of the next presentation, one of the greatest and yet one of the most misunderstood results in all of mathematics, Gödel's second incompleteness theorem. And with that, my presentation is ended.